Welcome back. So let's take a look at solving one of these net force type of problems. So, and of course, the best way to do this will be one, to read it, tease out the information from there that we need, and get ourselves a diagram or multiple diagrams that can help us out. So we have an 8 kilogram bag of coins being pulled upward. So we don't have to read further, and let's get ourselves a little visual of this. So we have a bag of coins being pulled upward. So I'm going to go ahead and draw that. Raise is 20 centimeters. So let me go ahead. I'm going to actually draw that a little bit more than that, just to have a good representation. So we have it's 8 kilograms. It's starting from rest, so that's initial velocity of 0.0 meters per second. And it's being raised 20 centimeters, so from there to there, we know delta y is 20 centimeters. And the time for that change in position is 1/2 of a second, 0.5 seconds. Okay. All right, so assume the acceleration is constant. So we know that there will be a force. All right, we know that there's going to be a force here going upward. Now let's assume that this acceleration is constant. So we're going to say that our acceleration is a constant. All right, so acceleration equals constant. Whatever that acceleration is, it is constant. All right. So now if we begin thinking about this, if this bag of coins is moving upward, I'm gonna come over here to the right side and just sort of draw out something to help visualize everything that's going on. Because remember, forces occur in pairs. So that means if this thing is moving upwards, excuse me, and this thing is also being pulled downwards due to gravity, right? Now notice I drew the downward arrow for gravity shorter than the upward arrow, and that's because if this thing is moving upwards, there must be a net force upwards. And we know that net force upwards, since we know that net force is mass times acceleration, then that has to be a net acceleration upwards, because there's acceleration downward, and there is, for our upward force, an acceleration, and the sum of those forces would be what the net acceleration is. All right. So over here on the left side, what we're really figuring out right now is the net acceleration. That's what we are figuring out. And so that would be mass times whatever we determine our net acceleration to be. Okay? So the vertical change in position, we know that we would have delta y equals vi delta t plus 1/2 a delta t squared. Excuse me. Since this is from rest, then we know that the initial velocity is 0. We can assume that. Okay? So that leaves us delta y equals 1/2 a, and we know that this acceleration would be a net acceleration, so I'm just going to put that there. Do we have delta y? We have time. We just need to figure out the net acceleration. So if we rearrange this equation now to solve for the net acceleration, then we know we're going to get twice whatever that displacement is times time squared. That's going to be our net acceleration. All right. So if we now let's solve this out. We've got 2 times delta y, 20 centimeters. So 20 centimeters, we know we need to be in meters. So that's 0.200 meters. Our time is 0.5 seconds. We have to square that. All right, so that's going to leave us. All right, so 2 times 0.2, that would be what, 0.4 meters. And 0.5 squared, so that would be 0.25, right? And of course, that's also going to be, let me rewrite that 5 a little bit better for you, seconds squared. And we can see right there that meters per second squared, that is our unit for acceleration. So we're doing this problem right. We're doing it. So far, so good. All right, so 0.4 divided by 0.25 gives us 1.6. So we're going to write out 1.60 meters per second squared. That's our net acceleration. All right. So we can figure out from that, we can figure out what our net force is going up. So the net force we know is the mass times the net acceleration, the mass being 8 kilograms, times our 1.60 meters per second squared net acceleration. That's going to give us 8 times 1.6, 12.8. All right, so that's kilogram meters per second squared, which we know is 12.8 newtons. So we can interpret that. Excuse me, 12.8 newtons. So now we can come over here. We know that right here, our net acceleration is 12.8 newtons, okay? I'm just erasing and replacing as we find out some data and some information here, okay? All right, so now, what's the upward force? And calculate the net force in the bag. So we've done that part, check. What's the upward force? So the upward force equals what? Well, to do that, we're going to need to figure out this part here. The downward is mass times the acceleration due to gravity. So you'll see it sometimes written as mg, or you could see it written as the lowercase a with the sub g right there. They both mean the exact same thing. All right. So if we figure out the downward pulling force here, we would have every variable we need along straight up and down along our force pairs to figure out our upward force just simply by just solving what the plugging into the sum of forces and just doing some basic algebra. All right, so well, let's figure that out. So we've got, let me separate this out a little bit. So we've got the force due to gravity is mass times the acceleration due to gravity. That mass is 8.0 kilograms. Acceleration due to gravity, 9.81 meters per second squared. All right, so 8 times, oh, that's divided. 8 times negative 9.81, we get a negative 78.48, and that would be kilogram meters per second squared, which we know is a negative 78.48 newtons. So now we know this part here. Now we know that this is a negative 78.48 newtons. All right. We have pretty much everything we need at this point because, let me separate this out. We know that the net amount of force is going to be equal to the sum of the forces. In this case, the sum of the forces is along the y-axis, which is equal to our upward force plus our downward force, okay? It's the sum of those forces. So our net force, all right, so we've got net force equals force up plus the force pulling downward. Well, if we rearrange this equation, we get the force up equals our net force minus our downward force. Well, we can see here that we have net force, we have our downward force. So our net force we know is 12.8 newtons minus our downward force, which is the negative 78.48 newtons. All right, so we've got 12.8, enter, minus negative 78.48. We get 91.28 newtons. That is our upward force. We now have this part right here solved. This right here is upward force is 91.28 newtons. And that makes sense, because if the upward force were equal to the downward force, the object would literally be staying still. It wouldn't be moving up, down whatsoever. We know the sum of the forces along X are 0 because it's not moving left or right. The mass is not accelerating one way or the other. So we know that the acceleration along X is 0, so we didn't have to worry about that in this problem here. So hopefully this kind of helps, seeing it step by step, sort of drawn out, just a way to approach doing this. To me, this makes the most logical sense. Thinking what's happening with your motion, knowing that forces occur in pairs, drawing out some sort of free body diagram like we have on the right-hand side that shows all that, and then interpreting the motion, knowing what we had as a net, and then just one step at a time, solving what we do not have until we have enough information to solve for what we need to find out. Hope this helped. Look forward to seeing you soon. Come back for another video. I'm going to have plenty for you. Always good learning with you. Take care, and we'll do this again soon. Bye.